All right, so it's about time and we start today. Ich werde am Anfang eine kurze Ankündigung auf Deutsch machen und dazu möchte ich gerne eine Folie teilen. So. Und zwar wird eine studentische Hilfskraft gesucht, beziehungsweise eine Studienassistenz für einen Studierenden unserer Fakultät, der sehr stark sehbehindert ist. Die Assistenz wird etwa 20 Stunden im Monat gebraucht und sollte sich gut auskennen mit, sagen wir mal, einigermaßen gut auskennen mit Mathematik, also den Stoff, der in den Mathe-Vorlesungen für BWL und VWL gemacht wird, den sollten Sie zuverlässig beherrschen, einigermaßen vernünftig. Sie brauchen jetzt kein Mathematiker oder Mathematikerin zu sein, also Sie müssen die Theoreme nicht beweisen können. Sie sollten aber in der Lage sein, das, was in den VWL, BWL, Mathe-Modulen verlangt wird, selber richtig verstanden zu haben. Das Ganze wird bezahlt. Ich kann Ihnen nicht sagen, zu welchem Stundensatz. Und die Assistenz besteht darin, dass Sie den Studierenden in die Vorlesung begleiten, teilweise mitschreiben, teilweise Präsentationsinhalte, die man normalerweise sehen müsste, um sie gut zu erfassen, zu erklären. Also zum Beispiel Grafiken zu erklären, wie die aussehen, wenn in Mathe Matrizen vorgestellt werden, sind die für Blinde schwer zu erfassen, wenn man sich das von einem Computerprogramm vorlesen lässt, weil es einfach eine große Menge von Zahlen ist. Und Sie sollten die Vorlesungsinhalte noch mit ihm zusammen vor- und nachbereiten. In der Ausschreibung ist angegeben, dass die Stunden flexibel gestaltet werden können. Das betrifft vermutlich nur die Vor- und Nachbereitung. Die Vorlesungen sind ja fix platziert. Das heißt, da sollte es dann schon möglich sein, dass Sie in die Veranstaltung mit reingehen. Dann war noch mit angegeben worden, dass Lehramtsstudierende, da weiß ich jetzt gar nicht, ob solche dabei sind, wahrscheinlich nicht, das als Praktikum anerkennen lassen können. Und wenn Sie Interesse daran haben, dann können Sie sich bitte melden bei Herrn Pascal Geweniger. Das ist der Student, um den es sich hier handelt. Die E-Mail-Adresse ist auf der Folie hier mit angegeben. Herr Geweniger ist sehr engagiert, und auch ein sehr netter Kerl. Und ich glaube, das macht auch sicher Spaß, ihn dabei zu unterstützen. Zusätzlich können Sie sich auch noch ein bisschen was dazu verdienen. Also das ist, denke ich, eine attraktive Ausschreibung. Und wer Interesse daran hat, soll sich bitte bei Herrn Geweniger direkt melden. Der kann auch weitere Auskünfte dazu geben. Das war die kurze Ankündigung von mir. Jetzt stoppe ich das Bildschirmteilen und übergebe das Wort erstmal an Herrn Lobeck, der das Studentische Wirtschaftsforum kurz vorstellen will, eine der Initiativen unserer Fakultät.
Moin, ihr Lieben, erstmal hallo zusammen. Vielen Dank nochmal an Professor Trede, dass wir das vorstellen dürfen. Ich teile einmal ganz fix meinen Bildschirm. Es wird nur 5 Minuten dauern. Erstmal ganz kurz zu mir. Ich bin Leon Lobeck, ich bin 23 Jahre alt und im 2. Mastersemester Volkswirtschaftslehre. Und wir haben eine Hochschulgruppe gegründet, das Studentische Wirtschaftsforum. Ganz kurz gesagt, wir bieten eine Plattform, auf der sich Studierende zu aktuellen politischen und wirtschaftswissenschaftlichen Themen austauschen und weiterbilden können. Eine tolle Definition. Grundsätzlich, wir machen Veranstaltungen, die finden natürlich leider derzeit über Zoom statt und laden uns dafür ausgewählte ExpertInnen und ausgewählte ReferentInnen ein und führen dann ein ganz lockeres Gespräch mit denen, was eigentlich gerade auf der Welt so los ist. Da werde ich euch aber gleich auch noch ein bisschen was zu sagen. Was ihr bei uns machen könnt, ist ganz grundsätzlich an unseren Veranstaltungen mitwirken, in der Planung. Ihr könnt Konzepte mit uns zusammen erstellen, ihr könnt aber auch einfach nur teilnehmen. Es besteht also überhaupt keine Pflicht, irgendwas zu machen. Ihr könnt natürlich auch selber als Moderator teilnehmen. Wir führen ja immer quasi solche Gespräche. Das ist dann so ein bisschen wie in einer Talkshow und das zertifizieren wir euch auch. Das heißt, ihr kriegt sowohl ein Zertifikat von uns am Ende des Semesters, wenn ihr teilgenommen habt, und noch ein viel besseres Zertifikat, in Anführungsstrichen, wenn ihr selber Moderator gewesen seid. Ich habe das auch schon gemacht mit Frau Professor Dr. Riedel. Da haben wir uns über die Auswirkungen auf die Economy nach der US-Wahl beschäftigt. Also was hat Biden eigentlich so vorgehabt und was hat er so gemacht und wie finden wir das? Das war eigentlich eine richtig coole Veranstaltung. Bisherige und kommende Veranstaltung, ich gehe noch ein bisschen mehr drauf ein. Einmal hatten wir noch den Fall GameStop, da haben wir uns mit dem Short-Selling beschäftigt. Ich weiß nicht, ihr habt das sicherlich in den Medien mitgekriegt. Das war auch richtig cool. Wir konnten nochmal richtig viel diskutieren und Herr Professor Schneider konnte da auch nochmal coolen Input geben. Da waren 70 Leute da, es konnten ganz viele Fragen im Chat stellen. Herr Schneider hat sich ganz viel Mühe gegeben, also das hat richtig Spaß gemacht. Dann hatten wir auch schon ein Kennenlerntreffen, da haben wir ein gemeinsames Knobelspiel gemacht. Ich habe mir einen Ökonomiequiz ausgedacht und haben uns dann zum Beispiel die Frage, wie viel Prozent des Warenexports der EU findet innerhalb der europäischen Grenzen statt. Man munkelt, wir haben ein Trinkspiel draus gemacht, da möchte ich mich von distanzieren, eventuell vielleicht ein kleines bisschen. Jetzt die kommende Veranstaltung, da freue ich mich ganz besonders drauf, das wird richtig cool. Da haben wir den Herrn Löschel eingeladen, den kennt ihr vielleicht auch, der ist in Deutschland ein sehr, sehr bekannter Klimaökonom und wir haben uns 2 Politiker eingeladen, einen von der FDP, Dr. Lukas Köhler, und eine Politikerin von den Grünen, Dr. Ingrid Nestle. Und da fragen wir uns ein bisschen, wie wir eigentlich CO2 einpreisen können. Ich freue mich da wahnsinnig drauf. Bei Dr. Lukas Köhler habe ich auch Praktikum gemacht im Bundestag. Das wird sicherlich eine richtig coole Veranstaltung, die Politiker auf die Wissenschaft loszulassen, beziehungsweise umgekehrt. Am 2.6. um 19 Uhr. Die Zoom-Daten seht ihr auch. Wo ihr uns ganz grundsätzlich finden könntet, ist auf unserer Webseite. Wir haben natürlich auch einen Instagram-Account. Folgt uns da gerne. Da machen wir immer wieder Ankündigungen, wenn neue Veranstaltungen sind, wenn wir neue Ideen haben oder wenn wir irgendwie was anderes am Plan sind und ihr euch da wenn ihr euch da beteiligen möchtet. Und natürlich haben wir auch noch, wir sind um 2100 so einen coolen Link, den könnt ihr einfach abfotografieren und dann kommt ihr sofort auf unsere Website. Und das war es dann auch schon quasi von uns. Ich würde mich freuen, wenn ihr auch mal zu einer Veranstaltung kommt. Ich freue mich wahnsinnig immer, wenn die da sind. Ich nehme immer richtig viel Wissen mit. Und das war's zu uns. Ich freue mich, wenn ich euch mal bei einer Veranstaltung sehe. Macht's gut. Und natürlich einen konsistenten Schätzer für die Koeffizienten der Regression, je nachdem, wie weit ihr schon seid. Dankeschön. Macht's gut, ihr Lieben.
Ja, vielen Dank, Herr Lobeck. Und ich kann wirklich nur noch mal alle aufrufen, sich in diesen studentischen Initiativen zu engagieren. Wir hatten ja schon eine Vorstellung gehabt vor 2 Wochen oder so, aber machen Sie das. Also das ist nicht nur eine gute Gelegenheit, andere Studierende kennenzulernen, sondern das ist auch inhaltlich interessant und bringt einen auch persönlich wirklich weiter. Also Kontaktadressen haben Sie ja, nehmen Sie das auch wahr. Alles klar. Gut, dann teile ich mal meinen Bildschirm wieder. All right, so let's start with empirical economics. Last week we talked about estimation, and we've seen that estimators have an asymptotically normal distribution or approximate normal distribution. And that means that we can perform statistical tests and we can do statistical inference in a very convenient standardized way. And today we have a first look at how these procedures actually can be done, can be performed. And we start with a standard test procedure, which is very important in empirical economics. That's the so-called t-test. So let's start with a concrete example. So let's suppose we are interested again in the running example we talked about before. So what is the relationship between class size and learning outcome in a school district? And we use the Californian school data test set again. So suppose someone has a theory or a hypothesis and postulates that class size, so the student-teacher ratio, actually does not have any impact on the learning outcome. So that is the hypothesis. And we could state this in formal terms, remembering that we presuppose that there's a linear relationship between the class size and the test score. So we can state this hypothesis in terms of the notation we introduced last week as the following. So I hope you can see my pointer. Since I can't see any one of you and have no feedback, please just, all right, okay, thanks, Andreas. We can state the hypothesis as simply saying that the slope coefficient of the regression line between class size and test score is 0. And that in effect means that it's a flat line, which means that the test score has no relationship with the class size. and the predicted outcome for the test score is the same beta naught in that case, irrespective of which value the class size actually has. This is a theory, or a hypothesis, and of course, a hypothesis or a theory can be true or false, and we are interested in this hypothesis, so we would like to test whether this relationship actually is compatible with the data, or rather, whether the data are compatible with this relationship here. So we want to check this hypothesis using the data set we have. And we ask ourselves, is the hypothesis compatible with the data? Of course, we do not assume that if we do an estimation, then that the estimated slope coefficient is really zero. It never will be, because it's a normal distribution, and the probability that a normal distribution has a particular value is just zero. So it will never happen. But if the estimated slope coefficient is very close to zero, then this hypothesis is compatible with the data. Okay, so this is what we would like to check. Do the data say that they are in line with the hypothesis, or do the data contradict the hypothesis in a very stark way? So, are the data compatible with the hypothesis, or do the data indicate that the hypothesis is actually wrong? This is what we would like to do. So we check the compatibility of the data with the hypothesis, or any economic theory for that matter. Okay, to do that, there's a formal framework which has been developed in statistics about 100 years ago. And this framework requires that we state the null hypothesis, that's the hypothesis we would like to test, and set up an alternative hypothesis. And in this course, the alternative hypothesis is always just the opposite of the null hypothesis. So if the null states that the slope is zero, then the alternative states that it's not. Or more generally, if the null hypothesis states that the slope coefficient has a particular value, say beta 1 naught, then the alternative just states the opposite and says it's not equal to beta 1 naught. Okay. It's also possible to test one-sided test. So in that case, we might check whether beta 1 is equal to some value beta 1 naught, and test again, sorry, this should be stated as greater than or equal to beta 1 naught, and the alternative would then be just the opposite. Okay. Then the test is performed again in a standardized way, and the standardization means that the first step is to compute the test statistic. The test statistic is a quantity that we then later use to evaluate whether the data and the hypothesis are compatible with each other or not. So the test statistic, in a way, quantifies how far away the data are from the hypothesis. And for the t-test, the test statistic always has a very simple structure. It's the estimated value, so the estimator. We subtract the hypothetical value, which often is zero. So in that case, this can just be dropped. And we divide the entire thing by the standard error. Remember, the standard error is the square root of the variance of the estimator. This is the standardized form of a t-statistic. So take the estimator, subtract, and the standard error is just the square root of the estimated variance of the estimator. We did that last week, but I will repeat that again today. Then for the particular example of the slope coefficient, the t-statistic has the following form. We take the estimator, so the estimated slope coefficient, beta 1 hat. We subtract the hypothetical value. So for the concrete example where the hypothesis states that the slope is flat, this would just be zero. And we divide the entire thing by the standard error of beta 1 hat. Okay, to do that, we need the standard error. The standard error is the square root of the variance of the estimator. the variance of the estimator tells us how volatile our estimation is. Are we generally close to the true value, or do the estimates scatter around the true value in a very wide fashion? So that's an important point, and the standard error can be computed from the data. So we have a way to actually quantify the precision of our estimation from the same data we use to really compute the estimator. And the estimator for beta 1 hat can be computed in the following way. So the variance of beta 1 hat, I think we introduced that last week already. The variance is this term here. So it's a complicated formula, but you will see today that we needn't care about how complicated these formulas are, since all of these formulas are implemented in standard computer packages. So we are going to use that, of course. But in any way, this variance here cannot be computed from the data, because here we have quantities which refer to the underlying unknown distributions, but we can estimate the variance of our estimator. Okay, so it's a two-step procedure, if you like. You have an estimator, which is a random variable because the data are random, and you can compute the variance of this estimator. But since we lack some information to compute the variance, we also estimate the variance of our estimator. And that's the formula down here. And all the terms in here are actually observable. So we have the axis, and we know the values of the axis, and we can compute the residuals. We've seen that last week. So all the terms here are observable, and we can compute the estimated variance of our estimator, beta 1 hat. And this is routinely done by standard computer packages and usually notated by SE for standard error. Okay, so I hand over to Andreas now. And as usual, if there are any questions, just switch on your microphone and ask, or use the chat. Okay.
All right, thanks a lot. Before I continue with the topic, let me just briefly announce that today, and I think from today on now every week, we have something like an active break that is supported to us by the Hochschulsport, because we are all sitting in front of our screens all day now, and there's no real possibilities to have some sports and some similar activities together. Hochschulsport offers active breaks in lectures, and since we have a lecture that is close past noon, I thought it might be a very sensible idea to do and to have such an active break in this lecture. So there should be someone coming over at 12:35, so in 2 minutes. So if you're already in the room, just make yourself, let us know that you're here, and then we might start that break. Unless that does not seem to be the case, I'm going to share my screen, and we will discuss how to perform the t-test in applied theory, and then you'll see later on how you can do that, and you'll see in the exercise how you will do that in R by just one single command. To perform the t-test, you would need basically 3 steps. The first one is, of course, compute the t-statistics. That's done for you in every, I got a message. Sure. Annika Körner, du bist anscheinend da. Es ist natürlich in Ordnung, wenn du auf Deutsch anleitest. Dann würde ich einmal kurz das Bildschirmteilen wieder beenden und wir können in die aktive Pause starten. Du kannst dich gerne unmuten und dann kannst du damit gerne beginnen.
Hallo zusammen, schön, dass ihr alle da seid. Ich bin Annika und wir machen jetzt zusammen 15 Minuten Dehnen und ein bisschen Kraftübung. Ihr dürft alle einmal gerne aufstehen und mitmachen. Wir fangen auch einmal direkt ganz entspannt an mit einer Atemübung. Dafür gehen wir ein bisschen in die Knie, atmen ein.
Sorry to interrupt. I think 15 minutes is too long.
Und atmen wieder aus. Und wir atmen wieder ein. Und atmen wieder aus. Und das Ganze machen wir noch zweimal. Wir atmen wieder ein. Nehmen die Arme mit und atmen wieder aus. Lassen die Arme einmal baumeln. Und ein letztes Mal ganz tief einatmen, die Arme mit zur Seite nehmen. Und wir strecken uns einmal so weit nach oben, wie es geht. Greifen nach den Sternen, stellen uns auf die Zehenspitzen. Sehr schön. Und wir atmen wieder aus. Sehr gut. Und dann geht es auch schon weiter mit einer Übung für unseren Nacken. Wir nehmen einmal unsere rechte Hand und legen sie an die linke Seite von unserem Kopf. Und wir ziehen unseren Kopf zur rechten Seite rüber, sodass wir an der linken Seite unseres Nackens eine deutliche Dehnung spüren. Das Ganze machen wir nur so weit, wie es angenehm ist. Wir wollen uns nicht verletzen. Und das halten wir noch. Ziehen schön zur Seite. Sehr gut. Und das Ganze halten wir noch für 5, 4, 3, 2, 1 und einmal lösen. Sehr gut. Dann einmal die andere Seite. Wir nehmen unsere linke Hand, legen sie an die rechte Seite unseres Kopfes und ziehen unseren Kopf nach links rüber, sodass wir wieder rechts eine deutliche Dehnung spüren. Machen das natürlich auch nur wieder so weit, wie es angenehm für uns ist. Sehr schön. Die Schulter zieht auch nach unten. Damit können wir die Dehnung verstärken. Und das Ganze halten wir auch noch für 5, 4, 3, 2, 1 und wir lösen einmal. Sehr gut. Dann geht es weiter mit ganz entspanntem Schulterkreisen. Wir kreisen unsere Schultern von vorne nach hinten. Sehr schön. Ganz entspannt. Schön bewusst kreisen lassen. Sehr gut. Und wir machen gleich einen Richtungswechsel, kreisen aber gerade noch von vorne nach hinten. Sehr gut. Und ein Richtungswechsel in 5, 4, 3, 2, 1. Und wir kreisen einmal unsere Schultern von hinten nach vorne. Sehr schön, die Arme auch mitnehmen. Und weiter ein- und ausatmen nicht vergessen. Sehr gut. Und das Ganze machen wir auch noch für 5, 4, 3, 2, 1 und lösen. Einmal locker machen, ein bisschen ausschütteln. Sehr gut, dann geht es einmal weiter mit einer Kraftübung für unsere Arme und Schultern. Wir strecken unsere Arme auf Schulterhöhe nach links und rechts. Guckt, dass ihr da ein bisschen Platz habt. Und wir machen ganz kleine Bewegungen nach oben und unten mit unseren Armen. Ganz bewusst, das ist eine gute Übung für die Schultern, aber auch für die Arme. Und wir können auch ein bisschen das Tempo erhöhen, werden schneller, machen kleinere Bewegungen nach oben und unten. Und das Ganze halten wir auch noch, sodass wir schön in unseren Schultern und in unseren Armen spüren. Und wir werden noch ein bisschen schneller. Sehr schön. Und noch schneller. Und das Ganze halten wir noch für 5, 4, 3, 2, 1 und einmal lösen, einmal die Arme ausschütteln. Sehr gut. Dann machen wir nochmal eine Übung für unsere Schultern und Arme. Wieder das Gleiche. Wir strecken unsere Arme nach links und rechts auf Schulterhöhe aus. Und diesmal beschreiben wir ganz kleine Kreise mit unseren Armen von hinten nach vorne. Ganz entspannt. Sehr schön. Und die Kreise können noch größer werden. Und die Arme bleiben auf Schulterhöhe. Und die Kreise werden noch größer. Ganz große, bewusste Kreise. Sehr gut. Und die Kreise werden wieder kleiner. Und das Tempo erhöht sich ein bisschen. Schön ein- und ausatmen nicht vergessen. Und dann machen wir noch einmal ganz kleine Kreise und das Tempo ganz, ganz schnell. So schnell wie es geht. Und das Ganze halten wir für 5, 4, 3, 2, 1 und lösen. Einmal die Arme ausschütteln. Sehr gut. Dann geht es weiter mit einer Dehnübung für unsere Schultern, aber auch für den oberen Rücken. Wir fangen an und legen unsere rechte Hand auf die linke Seite unserer Brust und die linke Hand streckt geradeaus nach vorne. Und wir rotieren einmal um 180 Grad mit unserem Oberkörper nach hinten. Der Blick folgt der Hand und die Hüfte bleibt da, wo sie ist. Wenn wir hinten angekommen sind, halten wir das kurz, spüren so deutlich eine Dehnung in unserer Schulter und gehen wieder nach vorne. Sehr schön und wir wechseln einmal die Seite. Die linke Hand geht auf die rechte Seite der Brust und der rechte Arm streckt gerade nach vorne und wir gehen um 180 Grad rechts nach hinten. Und wenn wir hinten angekommen sind, halten wir das kurz, Spannung im ganzen Körper. Und wir gehen wieder nach vorne. Und die Hüfte bleibt da, wo sie ist. Wir wechseln noch einmal die Seite. Der linke Arm geht wieder nach vorne und wir drehen uns nach links um 180 Grad. Und halten einmal. Sehr schön, spüren eine deutliche Dehnung in der Schulter. Und der Blick folgt der Hand wieder nach vorne. Und noch einmal die rechte Seite. Die rechte Hand streckt geradeaus nach vorne. Und wir gehen langsam und entspannt zurück. Und spüren deutlich eine Dehnung in unserer rechten Schulter. Sehr schön. Und der Blick folgt der Hand wieder entspannt nach vorne. Und wir lösen einmal. Sehr gut. Dann geht es weiter mit einer Übung für unseren Rücken. Ich stelle mich seitlich auf, um euch das zu zeigen. Wir stehen ungefähr schulterbreit. Gehen ein bisschen in die Knie sollen aber nicht über die Zehenspitzen gucken und machen einen geraden Rücken und die Arme gehen auch gerade nach oben. Und wir ziehen unseren Bauchnabel nach innen, sodass wir im ganzen Körper eine Spannung haben und eine schöne Dehnung im Rücken spüren. Machen schön Spannung im Rücken. Sehr schön und das halten wir. Sehr gut, ein- und ausatmen nicht vergessen. Und das Ganze halten wir noch für 5, 4, 3, 2, 1 und lösen. Sehr gut. Dann noch eine ganz entspannte Übung. Ich stelle mich wieder seitlich auf. Wir fangen an und legen unser Kinn auf die Brust. Die Arme baumeln weg vom Körper und wir gehen Wirbel für Wirbel nach unten, lassen uns ganz entspannt nach unten runter und lassen uns einmal baumeln, wenn wir unten angekommen sind. Und wir gehen wieder ganz entspannt Wirbel für Wirbel nach oben. Das Kinn bleibt auf der Brust, die Arme gehen mit und das Kinn geht weg von der Brust und der Blick geht nach vorne. Und das Ganze machen wir noch einmal. Wir legen wieder unser Kinn auf die Brust und gehen Wirbel für Wirbel nach unten. Die Arme baumeln lassen. Sehr schön. Und dann, wenn wir unten angekommen sind, lassen wir uns einmal ganz entspannt hängen. Entspannen uns. Sehr schön. Und wir gehen wieder nach oben. Wirbel für Wirbel. Das Kinn bleibt weiter auf der Brust. Und wir richten uns wieder auf. Und der Blick geht wieder nach vorne. Sehr gut. Dann wollen wir einmal was für unsere Oberschenkel machen, die ein bisschen kräftigen oder generell für die Beine. Dazu stehen wir ein bisschen ungefähr schulterbreit und wir wollen Ausfallschritte also quasi eine Squat-Variation nach rechts und links machen. Wir fangen an mit der rechten Seite. Dazu gehen wir einmal nach rechts rüber. Das linke Bein bleibt durchgestreckt, gehen rechts in die Knie, spüren so auch links schon eine Dehnung im inneren Oberschenkel und schieben uns zurück zur Mitte. Und das Ganze machen wir nochmal. Wir gehen nach rechts rüber in die Knie und schieben uns zurück zur Mitte. Sehr gut, das Ganze machen wir noch 4-mal. Und zurück. Noch 3. Und zurück in die Mitte. Und noch 2. Und ein letztes Mal schön tief gehen und zurück in die Mitte pushen. Sehr gut, dann wollen wir einmal die Seite wechseln. Wir schieben uns jetzt nach links rüber. Heißt, wir gehen links ein bisschen in die Knie. Das rechte Bein bleibt durchgestreckt, sodass wir rechts auch eine Dehnung spüren. Und wir schieben uns zurück in die Mitte. Und wir gehen wieder nach links rüber und schieben uns hier auch wieder zurück in die Mitte. Das Ganze machen wir noch 4-mal. Rüber, schön in die Knie und zurück pushen. Noch 3-mal. Runter und zurück. Und noch 2-mal. In die Knie und zurück pushen. Und ein letztes Mal. Schön in die Knie, dass wir eine Dehnung spüren. Und zurück pushen. Sehr gut. Dann wollen wir natürlich auch was für unsere Waden machen. Ich stelle mich seitlich auf. Wir stehen ungefähr schulterbreit. Und wir wollen einmal unser Gewicht auf unsere Zehenspitzen verlagern. Waden und Beine anspannen. Und halten das kurz. Und setzen wieder ab auf unsere Fußsohlen. Und wiederholen das. Verlagern unser Gewicht auf unsere Zehenspitzen. Halten das, merken, dass unsere Waden stramm werden und setzen wieder ab und wiederholen das noch 3-mal. Gewicht schön auf die Zehenspitzen verlagern und halten und wieder abrollen auf die Fußsohlen und noch 2-mal Gewicht auf die Zehenspitzen verlagern. Schön Spannung in den Waden. Und Gewicht wieder abrollen. Und ein letztes Mal auf die Zehenspitzen. Spannung halten und abrollen. Sehr gut. Dann noch etwas für unsere Füße. Wir wollen einmal abwechselnd das Gewicht erst auf das rechte Bein mit den Zehenspitzen und dann zieht das linke Bein nach, sodass wir einen Wechselschritt haben, bei dem wir das Gewicht abwechselnd auf Zehenspitzen und Fußsohle verlagern. Das machen wir jetzt auch ganz entspannt. Rechts und links, rechts, links. Weiter entspannt. Ein- und ausatmen nicht vergessen. Sehr gut. Können auch noch mal ein bisschen schneller werden. Sehr gut. Und das Ganze machen wir noch für 5, 4, 3, 2, 1 und lösen. Sehr gut. Dann wollen wir noch einmal unsere Füße kreisen lassen. Dafür verlagern wir unser Gewicht auf das linke Bein und das rechte streckt nach vorne. Die Hände können an die Hüfte gehen und wir kreisen von außen nach innen unsere Füße. Sehr schön. Und wir machen gleich auch einen Richtungswechsel. Dann kreisen wir von innen nach außen. Sehr gut. Und den Richtungswechsel machen wir in 5, 2, 1 und wir kreisen von innen nach außen unseren Fuß. Sehr gut. Und das Ganze machen wir auch noch für 5, 4, 3, 2, 1 und lösen. Sehr gut, dann einmal die andere Seite. Wir verlagern unser Gewicht auf die rechte Seite, aufs rechte Bein und kreisen von außen nach innen unseren linken Fuß. Ganz entspannt, schön bewusst kreisen lassen. Sehr gut. Und hier machen wir auch sofort einen Richtungswechsel und kreisen von innen nach außen in 5, 4, 3, 2, 1 und Richtungswechsel. Wir kreisen unseren Fuß von innen nach außen. Sehr gut. Und das Ganze machen wir auch noch für 5, 4, 3, 2, 1 und lösen. Sehr gut, dann wollen wir noch mal einmal alles ausschütteln. Arme, Beine, Füße locker machen. Und zum Abschluss wollen wir noch einmal tief einatmen, gehen wieder in die Knie. Nehmen die Arme mit zur Seite und atmen wieder aus. Und atmen wieder ein. Und wieder aus. Und ein letztes Mal ganz tief einatmen. Und wir strecken uns einmal nach oben, so weit wie es geht, greifen nach den Sternen, stellen uns auf die Zehenspitzen und wir atmen wieder aus. Sehr gut, ja, das war es dann auch schon. Die 15 Minuten sind schnell vorbeigegangen. Ich hoffe, ihr fühlt euch jetzt ein bisschen gelockert, hattet Spaß und vielleicht sehen wir uns dann ja nochmal. Tschüss.
Okay, vielen Dank. Perfect. Thanks for that activation during the lecture. Although it took a little longer than I anticipated, but nevertheless, thanks a lot. Let's now continue after that short break. Let's make up for the time in a manner. Where we left off, that is by how to perform t-tests yourselves. Mr. Trede just told you how to compute the t-statistics by the formula on the slide on the previous slides. And what we need to do, or what the computer does for us, is it does all that automatically. So the only thing that we see in the end is the actual t-statistics. We don't need to compute that by hand, but if we'd like to do that, then we can compute it by the formula you can see here. So our slope coefficient, or estimated slope coefficient, minus our hypothetical value divided by the standard error that we just estimated from our slope coefficient. The second step is, based on our t-statistics, we need to decide whether we need to either reject the null hypothesis or whether we cannot reject it, so whether the data is not strictly against the null hypothesis. And we can do so at the 5% significance level if the absolute value of our t-statistics exceeds the value of 1.96, a value you have encountered in previous lectures before, and in the previous week we've encountered that value before as well. And that, if you remember, comes from the idea that approximately in large samples the t-statistics is standard normal distributed, and that values that exceed 1.96 are, at least by random sampling, very unlikely. So we are pretty sure that, at least if the assumptions that we made for a model hold, that the null hypothesis is in very stark contrast to our data. And the third step, well, not the third step, but second and third item on this list are more or less equivalent. We can compute the p-value, so the probability that the absolute value of a standard normally distributed random variable is larger than our t-statistics, or the absolute value of our t-statistics. We can compute that, and that is, so to speak, the lowest significance level at which we could reject our null hypothesis. So the value, the probability that we would observe a test statistic only under random sampling, so only because we draw a different sample, that is in absolute value larger than the current t-statistic we computed. So this approach only works for large samples, because we only for large samples we can state that our t-statistic is approximately normally distributed. In our example of student-teacher ratio and test scores in California, we have seen that the estimated regression line was had an intercept of roughly 700, and then a slope coefficient of student-teacher ratio of minus 2.28. So for each additional student, test score decreased by roughly 2.28. The standard error we see, or the standard errors we see for our intercept is 10.4, and more importantly, for a slope coefficient, the standard error from our statistics software package, maybe R, maybe others, is 0.52. With this, we can then compute directly the t-statistics for the hypothesis that class size, so STR, does not have an influence on test score at all. So the hypothesis is beta 1 is equal to 0, because if it's 0, then class size doesn't have any influence. To do this, we take our estimated value, it's minus 2.28, subtract 0, divide by 0.52, and we get a t-statistics of minus 4.38, which is in absolute value obviously larger than 1.96, so we can reject the null at the 5% level. We can even reject at the 1% significance level because the t-statistics is even larger than the critical value of 1%, that is 2.58. So we're pretty sure that if our assumptions hold, and that is a big if here, then we have a significant influence of class size on learning outcome. Usually you will also see next to the t-statistics, and Mr. Trede will show you that in a couple of minutes, we'll also see the p-value of the statistics. In our case, the p-value is very, very low. It's 0.000012. So the probability for a standard normal, a random variable, so by random sampling, randomly receiving a t-statistics larger than the one we just received is very, very small. So in this case, we have reject the null hypothesis at very low significance levels. If we want to see the p-value graphically, you can do that by first of all plotting the density curve of the standard normal. And then the p-value is the area under the curve left of minus the absolute value of the t-statistics plus the area under the curve right of the absolute value of the t-statistics. Now, as I said, the p-value here is 0.00 and so on, very, very small. So the area under these two parts of the curves are obviously very, very low as well. So you can't really see that in here, but now just consider another t-statistics, in this case with the value -1, with the value -1, and then the p-value of that is of course the area under the curve to the left of minus the absolute value of the t-statistics plus the area to the right of the curve of plus the absolute value of the t-statistics. And that in this case is roughly 30%. So from minus infinity up to 1 is 15%, and from +1 up to plus infinity is also roughly 15% the area under that curve. In this case, we have a very high p-value, and we cannot reject the null hypothesis at any sensible significance level. If we invert the idea of a hypothesis test, so we're not going to check a single value whether it is consistent with the data or not, or whether we have to reject that value, but we do it the other way around. If we want to find out a set or a range of all the values that are consistent with the data, then we can build a confidence interval. The most common confidence interval to build is the 95% confidence interval. So the one regarding the one that is with respect to the 5% significance level. And we can compute these confidence intervals. So the range of all slope coefficients that are consistent with our data by taking our estimator and adding and subtracting 1.96, so the critical value that we've seen before, times the standard error of our estimator. In this case, for our slope coefficient, we take our slope coefficient, the estimator of the slope coefficient. We subtract we subtract 1.96 times the standard error to get a lower bound for the confidence interval, and we add 1.96 times the standard error of our estimator to get an upper bound of these confidence intervals. Obviously, for other confidence levels, so if you want to have a 99% confidence interval, you need to switch that value 1.96, in this case to 2.58. Or if you want to have a 99.9% confidence interval, you have to include an even higher value there. So let's do that in application. In our student-teacher ratio example, our estimated regression line again is the one we've seen before. So we have a slope coefficient of -2.28. We have a standard error of 0.52. Then our confidence interval is -2.28 plus -1.96 times 0.52, and which gives us a range of possible coefficients that is consistent with our data, ranging from -3.3 up to -1.26. These are all obviously smaller than 0. You can see here the 0 is not included into that confidence interval, which is something we would expect because we have already seen that we should and we must reject the null hypothesis of beta 1 being 0 at the 5% level. So the 0 cannot be inside the range of values that we would not reject. So if you don't see a value inside your confidence interval, then you can be sure at that confidence level that you can reject the null hypothesis of this slope coefficient being that value. Okay, that's it from my side for now. I'm again going over to Mr. Trede, who is going to show you how to present regression results in both scientific works and in this course.
Okay, can you just stop sharing your screen, please?
Yep.
Thanks. Right. Okay, so you have seen now how to perform a t-test, and you have seen how to perform constructing confidence intervals. The most difficult to compute ingredient for both t-tests and confidence intervals is obviously the standard deviation. We've seen the formula for the standard deviation, and it's a complex one, but luckily it's implemented in standard computer packages. And I'd like to continue now to explain you how the results of an estimation are typically presented in a scientific context. So, oops. Right. We've already seen the estimated regression line for the class size example, and we've seen that the point estimated for the intercept is roughly 700, and the slope coefficient is roughly -2.3. So the main part of this equation here is what we have already seen before. And the standard way to report the standard errors in regression analyses is to just put them in brackets below the point estimates. Okay, so we have the point estimate here, 700, and the standard error is 10.4. We have the slope coefficient -2.28, and the standard error is 0.52. That's the standard way to report a regression line. And as you have already seen that the standard errors are important to do confidence intervals and t-tests, this information here is already sufficient to perform the interesting t-tests and to compute confidence intervals. So this notation shows what the estimated regression line is. It tells us what the standard error for the intercept is. And it also tells us what the standard error for the slope coefficient is. And if you need a very rough rule of thumb estimate for a confidence interval, say of the slope coefficient, then you just take the point estimate -2.3, and you add and you subtract roughly 2 times the standard error to obtain a 95% confidence interval. So the standard error is a half, say 2 times that is 1. Then a very rule of thumb, very rough confidence interval would be minus 3.3 up to minus 1.3. This is not exact, but it's a nice rule of thumb. And just looking at this result here allows you to very quickly, in your head, calculate confidence intervals or perform a t-test. All right. Right, there's a standard way to print the output of regression analyses by computer software packages. And it's really standardized, which means that it doesn't really matter which computer program you use, the output will look very much alike in any case. So in a generic way, the output looks like this table here. You have information about the dependent variable on the left-hand side. So for instance, the test score. And then you have a main table where the estimation results are subsumed. The first column is usually the estimator, or the estimate this should read rather. It's because it's not a random variable, it's just a number. And here we have the 2-point estimates that we have already seen before. This one is wrong, it should be minus 2.28. And the point estimate for the slope is 698 for the intercept is 698.9. Then in the second column, we have the standard errors, 10.4, we've seen that before, and roughly a half, we've seen that before as well. Then the next column is the t-test statistic for a test against 0. So in that case, the hypothetical value is just 0 for all the coefficients we look at. So the t-test statistic is the point estimate minus the hypothetical value, which is 0. So just 698.9 divided by the standard error, 10. So in that case, we get 66.8. And that's a very large t-statistic. You know that a t-statistic is already considered too large for a 5% t-test if it's larger than 1.96. And 66 is much, much larger than that. So the p-value is exceedingly small. It's practically 0. So it's, well, just 0 in that case, more or less. And the t-statistic for the slope coefficient is the point estimate minus 2.28 divided by the standard error, and that results in minus 4.35. And again, this is well, in absolute values, this is a large value in absolute terms because 4.3 is larger than 1.96 as well. And again, we have a p-value which is very, very small. This is the main part of all the computer outputs. So it doesn't really matter which program you use, the output will look roughly like this. And then depending on the program you have, you get further results, for instance, the R-squared that we have encountered last week, or the standard error of the regression that we have also encountered last week. So let's have a look at standard computer packages. First, R. So what does the computer output for linear regression in R look like? And the output looks like this. First, you get well, repetition of the command you actually typed in. You can see that here you regress the test score on the class size. It's a weird notation, but you will get used to that in the exercise classes. And then we have the main table. First column, the estimates. Second column, the standard errors. Third column, the t-values. And finally, the p-values. And you can see here that the t-values are different from the ones on the previous slide and from the ones that we've computed. And the reason for that will become clearer later on. So there's a different formula for computing the standard errors here. And we will talk about that in a couple of minutes. Then we have additional information about the R-squared. That's here, 0.05. The adjusted R-squared, we haven't talked about that yet. And the standard error of regression is 18.58. There's a different way to compute this table in R. That's the one that you should use in this course. And the results given here are exactly the ones that you've seen on the previous slide, on the generic table. So these are the standard errors which are correct using the formulas that we use in this course here. Okay? And again, you have this standard table. Right, if you use different computer packages, you will get roughly the same output. So if you use Python, for instance, an OLS regression result output would look like this. So there's not the main table that I've shown you before. Here we can find the R-squared, the adjusted R-squared, and so on. And then on the next slide, the rest of the table. And again, here we have the main part. We have the column of coefficients, the point estimates. We have the column of standard errors. We have the column of t-values and the column of p-values and some other statistics which are not interesting for us now. Okay, so the main part of the table again is the same as the one we've encountered before. If you use eViews, which is also available at this faculty, you get again this main part of the table. You can see here the dependent variables, the test score, the intercept, the slope coefficient for the class sizes, the standard errors, the t-values, and the p-values. Then you have the R-squared and the standard error of regression, which is 18.5. And if you use Stata, which is also available at this faculty in the computer pools, you regress the test score and the class sizes, and you get again the standard table for the output. You have here the column of estimates, point estimates, ordered in a different way. You have the standard errors, you have the t-values and the p-values, and in addition, some confidence intervals. Then you have the R-squared, which is here, and the root mean square error. That's what we call the standard error of regression, 18.5 or 18.6. So again, it's roughly the same. And finally, you can even use Excel. In that case, you get the same output again. So you have the column of point estimates, the column of standard errors, the t-values, and the p-values. All right, so this is what the outputs look like in different computer packages, and always there's some main table in that, and the main table in particular contains the coefficients, the point estimates of the coefficients, the standard errors of the coefficients, and in addition the t-values and the p-values. All right, I'll hand over to Andreas again.
Welcome back. Up to now, we have only talked about continuous regressors, continuous exogenous variables, which makes sense because up to now we've been talking about the class size, and class size in a single class is obviously not a continuous variable, it's a discrete variable because you can only have full students in a class. But put together in a whole school district, class size obviously is a continuous variable. Can take on any value between a certain lower and a certain upper boundary, but it's a continuous variable. Sometimes it's also very interesting to not look at continuous variables, but only to look at discrete variables, and more specific at variables that can only take on two values. Usually we code that as 0 and 1s or as true and false values. And we could call such a variable a binary variable or a dummy variable. So sometimes the exogenous variable is, for example, the gender of a person, that might be coded as a binary variable with a 1 if a person is a woman and a 0 if a person is a man. Or in experimental data, we can code with a 1 that a person has been given a certain medication, and with a 0 if that person only got the placebo or didn't get a medication at all. In our class size context, it might be a good idea to have a first look at, or to think that maybe there is a certain threshold, that below that threshold there is a good performance of students, but above that threshold we the performance gets poorer and poorer, and we see much lower test scores. So we could state that our dummy variable, our binary variable, might be 1 for small classes and might be 0 for large classes. So we need to define that threshold in a minute, but we have a variable now that does not count student-teacher ratio anymore, but that counts whether or not the class can be considered small. Now, what's the interpretation of such a slope coefficient of such a regressor if the regressor is a dummy variable? Well, still, our regression equation is still the same. Y is still determined by our intercept plus beta 1 times xi, plus our error term. But that can now be rewritten because we state that x can only take on 2 different values, namely 0 and 1. So we can rewrite that same equation as yi is equal to beta 0 plus the error term. If x is 0, then of course beta 1 times 0 is 0. And that term vanishes from the equation. Or we can say that if x is 1, then obviously yi is beta 0 plus beta 1 plus our error term. So beta 0 becomes the expectation of yi when x is 0. So for example, if we have a large class, and beta 0 plus beta 1 is the expectation of yi when x is equal to 1. So when we have a small class, then beta 1 plus beta 0 is the expected test score of that small or of a typical small class. Let's have a look at that in other words, so in a more mathematical notation. So the conditional expectation of y, given that x is 0, so given that we have a large class, is beta 0, and the expectation of y, of test score, given we have a small class, so x is equal to 1, is beta 0 plus beta 1. Now, if we on both sides of this equation subtract beta 0, we get on the right-hand side just beta 1. So beta 0 minus beta 0 plus beta 1 is beta 1. And on the left-hand side of this equation, we get the expectation of yi, given we have a small class, so x is equal to 1, minus the expectation of y given x is 0, so given we have a large class. So beta 1 now measures the difference in y, in our test score, between those two groups. So the expected difference of test score between small classes and large classes. So beta 1 shows us how much higher is the expectation of y when x is equal to 1. How much higher, of course, only if beta 1 is positive, or how much lower is the expectation of y when x is equal to 1, of course, if beta 1 is negative. Let's have a short look at that in our context of student-teacher ratio. We can define our dummy variables, and usually it's a convention that we don't write down dummy variables as x variables because we only denote continuous regressors by x, but we denote a dummy variable by capital D. So instead of x, if you read a D in a regression equation, you should know that this is always, or this usually defines a dummy variable and not a continuous variable. Now, the mathematical notation and definition of D is 1 if str is smaller than 20. So a small class is defined as having less than 20 students, and di is 0 if str is larger or equal to 20. So whenever we have at least 20 students, we call this a large class. And other ways, it's a small class. And then our software package computes the regression. We see that the estimated test score is 650 plus 7.4 if the class is small, so plus 7.4 times D. So the difference of the expectations of both of these groups is 7.4. So in expectation, we see that large classes, so classes with D equal to 0, have a 7.4 lower test score than small classes, meaning that large classes on average get a test score of 650, And small classes on average get a test score of 657.4. Now, can we test whether this coefficient of D is significant now or not? We can directly do that. We have already seen the framework for hypothesis testing, and we can apply that, of course, to any slope coefficient, not only to slope coefficients of continuous variables, but also to slope coefficients of binary variables. So we use the same framework. We set up our two hypotheses, the null hypothesis, that there is no significant there is no significant effect of being in a small class versus being in a large class, and the alternative hypothesis, it just states that there is that this coefficient is different from 0. Our t-statistics we can compute that the same way we did before. So our estimate divided by the standard error, that is our estimate for the t-statistic. That is 4.1 here. That obviously is larger than 1.96. It's also larger than 2.58. So we can reject that null hypothesis even at the 1% level. So if our assumptions are met again, we are pretty sure that there is a significant difference between these two groups, between the performance of these two groups in our standardized test that we've seen in the data. Okay, there is some question. No, okay, perfect. Then I'm going to give over again to Mark.
Thanks. All right, so the next topic concerns an assumption which refers to the distribution of the error terms. And it's very strange terminology. We talk about hetero and homoskedasticity. And the distinction between these two different types of variances for the error terms is relevant because it tells us something about different ways to compute the standard errors. And as you have realized in these standard tables for different computer packages, there were two kinds of outputs. One which is compatible to what we are doing in this course, and the other one which is different. So for instance, the standard Python output is different from what we would compute using the formulas in this course, and the standard output in Excel and R as well are different from what we need in this course. And the reason for that, as I announced, will be dealt with now, and that's to do with hetero and homoskedasticity. What do we mean by these two terms? Well, homoskedasticity means that the variance for the error term is constant for all values of the regressor. So no matter whether the classes are small or large, the variance of this idiosyncratic shock in that school district is always the same. That's meant by homoskedasticity, while heteroskedasticity means that the error terms are not homoskedastic. So there might be different variances for the error term depending on the value of the regressor. So for instance, if class sizes are very small, then the variance of the error term might be small. So the points are quite close to the regression line. And if the classes are large, then the variance might be large and the terms scatter around the true regression line very widely. So this is what is meant by homo and heteroskedasticity. We have a little R program to illustrate that, but let me put that back a couple of slides, okay? Right. So since class sizes and heteroskedasticity are not that relevant probably, there's a different example here to illustrate what is meant by heteroskedasticity. Suppose we are interested in the hourly wage depending on the years of education, Ausbildungsdauer. And here we have data from the panel study of income dynamics. That's an American data set, US American data set, where a number of individuals have been followed for very many years. I think they started in the 70s. And then we have data in this case for 2003, about hourly wages, and we have data about education, years of education. And if you plot that, then you can see that individuals with very low numbers of years of education tend to have very small hourly wages, while individuals that have a large number of years of education tend to have higher hourly wages, but also the wages scatter around much more than down here. So the variance of the error term down here is very small, and the variance of the error term up here is very large. This is meant by heteroskedasticity. So the variance of the error terms, the dispersion of the cloud of points depends on where you are on the regression line. All right, so what happens if we assume homoskedasticity? We haven't assumed that yet. So in this course, we usually assume heteroskedasticity, which is the more complicated case, but of course the more realistic case. But suppose for a moment that we assume homoskedasticity. In that case, we can theoretically derive, and if you're interested in that, you're really invited to attend the course, the module on econometrics, where we really derive these results. If we have homoskedasticity, then we can show theoretically and really mathematically that OLS estimators, the one that we have derived, are the best linear unbiased estimators, which means that there's no linear unbiased estimator which has a smaller variance than the OLS estimator. So in a certain sense, OLS estimators can be shown to be the best possible estimators there are if we have homoskedasticity. Okay? And in that case, also the formulas for the estimator's variance and the standard error simplify dramatically. So remember, these formulas look really, really ugly. But if you assume homoskedasticity, then a lot of terms cancel, and the variance of the standard, the variance of the estimator, the slope, boils down to this little ratio of the variance of the error terms divided by the variance of the axis, the regressor, times n. So this is really a very simple formula and easy to calculate. So we have, in effect, two different formulas to calculate the standard error of the slope coefficient. Under homoskedasticity, it's this relatively simple term here, and this can be, of course, computed by a computer. And under heteroskedasticity, that's the case we assume in this course, generally. We have this more complicated formula down here. That's the one we've already encountered last week. Okay? So there are two different ways to compute the standard errors. And as you have seen, the standard errors are really, really relevant if you want to calculate the t-test statistic or perform or compute a confidence interval. So there are two different ways, and most standard computer packages compute the standard error using this formula up here. And that's not always correct. So if you use Excel, if you use Python, if you use standard R, or most other standard computer packages, you will get a standard error computed this way here, which is not correct in our setting. And if you want to compute the standard error using the formula down here, then you have to tell the program that you want to do that. You're going to learn how to do that in R. It's also easy in Stata. It cannot be done in Excel, for instance. So Excel usually is not an option to do empirical economics. It could be done in Python, of course. And it can also be done in eViews. Okay, so there are two different ways. And of course, the standard errors computed by the upper formula and the lower formula are different in general. And how much they are different will be shown in a little application by Andreas now.
Okay, thanks. Let me just show you a little R program. It's this little simulation study that I will go briefly over the code, and then we'll look at the plot that this generates. We have a simulation that runs 1,000 times. So we 1,000 times generate data run a regression, look at our standard errors, and compare the standard errors of the method under homoskedasticity to the method under heteroskedasticity. So basically, we initialize all our values, our regressors x. Then we go over a loop over all these 1000 iterations, and we generate here our error term. Artificially, of course, that's something we don't have in real-world applications, but this is just a simulation to illustrate the problem of heteroskedasticity and the problem of neglecting heteroskedasticity. So we can, in fact, generate error terms. And we state that the error term has a mean of 0, so that is perfectly fine, but has a standard deviation that is equal to x. So the larger we are in our, for example, years of education grid, the larger is the standard deviation of our error term. So just the same thing that you saw on this little graph a few slides before. And then y is defined as 10 plus 3 times x. That doesn't really matter. What our true value of the slope coefficient is here, plus our error term. And what we do now is two things. First, we run a regression, use the coef test function to run a t-test on all the variables in the regression. And with this brackets 2,2, we extract the standard error of the second t-test, so the t-test of our slope coefficient. This formula here works, only applies homoskedasticity. And now we can do the same thing with heteroskedasticity by just stating that VCOV, so the variance covariance matrix we use, is heteroskedasticity robust here. So we have a heteroskedasticity robust variance covariance matrix. And let us just run this little snippet. Just takes a second to run. And then we can plot the standard errors of under homoskedasticity against the standard errors under heteroskedasticity. And I hope that you can see the plot right now down there. We can see on the x-axis the estimates for the standard errors of our regression coefficient under homoskedasticity. And on the y-axis, the standard error, the correctly estimated standard error under heteroskedasticity, because that's what we have, because our error term does not have a constant variance, but the standard deviation and the variance of our error term deviate in the value of our regressor. So if these two standard errors were identical, they would be on a 45-degree line, and that line is depicted here. It doesn't look like a 45-degree line, but that is just due to the scale of the axis here. But in fact, this line here is 45 degrees. It has an intercept of 0 and a slope of 1. So if standard errors when neglecting heteroskedasticity would be the same as when taking the potential heteroskedasticity into account, then all these standard errors would be on this line. But as you can see here, the standard error under heteroskedasticity underestimates the standard error we would obtain if we correctly applied a heteroskedasticity robust method here. In other words, the t statistics and would be overestimated because we are working with too small standard errors here, and our p-values would be too low, so it would indicate much more significance as we have in fact. Okay, I think that was what this R program should tell you, and I'm going back over to you.
Right, so we can see that it does make a difference whether we use the upper formula or the lower one. If we use the upper formula in the case where actually there is heteroskedasticity, then we get we get a standard error which tends to be too small. It's not always the case, it depends on the data at hand, but it tends to be too small. And a small standard error indicates that the estimation is relatively precise, but in that case, that's misleading because it's only computed that small because you assume homoskedasticity but this assumption is actually not true. So in that case, you have a serious problem. And this problem is important because the default in most statistics software is the assumption of homoskedasticity. So, oops, there's a typo here. The default must be changed to obtain standard errors under heteroskedasticity. That's not possible in some computer packages, for instance, Excel or SPSS. So in that case, it's really not advisable to use these programs here for empirical economics, but most other programs allow to change the setting, and you should do that. So what happens if the software assumes homoskedasticity, but in reality there is not? So in reality that's heteroskedasticity. In that case, we've just seen that the software computes the wrong standard errors. And they tend to be too small, not always, but they tend to be too small. So a wrong standard error implies that the t-statistics are wrong, so the test results are wrong, and also the confidence intervals are wrong. So it's really a serious problem. You don't really realize that you have this problem because the calculations are done just routinely by the computer, but the output you get is simply nonsense. So if you use the homoskedastic formulas, but if you are in a situation where you have heteroskedastic data, and that's usually the case, then you obtain the wrong standard errors. The other way around, if you use the heteroskedasticity formulas, so the more complicated one, but in reality you have homoskedasticity, then there's not really a problem, because homoskedasticity is just a special case of heteroskedasticity. So the formulas for heteroskedasticity also work under homoskedasticity. There's a certain lack of precision, and you might get more information out of the data set, but at least the formulas are not wrong. So there's no problem if you assume heteroskedasticity, but this assumption is not really warranted. So for large n, both these formulas yield the same results under homoskedasticity. And therefore the conclusion is that if you're not really sure that homoskedasticity is the correct assumption, then you should always use the heteroskedasticity option in your software. You're going to learn how to do that in R. This is really an important part of this course. You can also do that in Stata, in eViews, and in other software packages, but we only use R in this course here. All right. So let me briefly summarize what we did so far. So we started with our running example of the class sizes, and we ask ourselves, what is the effect of reducing the class size by 1 on the test scores? And we did that by collecting data from different school districts in California. We then ran a regression, and the question is, well, we got point estimates. So the point estimate for the intercept was 700, and the point estimate for the slope was minus 2.3. But does this regression analysis really yield an answer to the question we posed at the very outset, to the policy question? So if we reduce the class sizes by 1, would the test scores really increase by 2.3 on average? Is this what we can conclude from our regression analysis? And this is where our reasoning comes in. So just running a computer package is not enough. You have to think about the results. And the answer here is no, because districts with lower class sizes, with smaller class sizes, tend to have fewer learning facilities for the students in general. So, for instance, the schools are less well equipped with computing facilities. There's a poorer general environment in those areas. So other regressors, which also impact on the learning outcome, tend to be different in those districts where we have smaller class sizes. Well, this is an example of large class sizes. Sorry, I swapped that. But in any case, so the class size tends to be correlated with other regressors that also impact on the learning outcome. So in that case, the error term would be correlated, or there would be a non-zero covariance between the error term and the class sizes. And here it's relatively easy to think about this problem. We would assume a negative correlation or covariance between these two terms. So small classes tend to have a large error term, positive error term, and large class sizes would be associated with a negative error term. And this assumption is really harmful because we assumed for our derivations, assumption number 1, which told us that the expected error term is 0 for any x. But if there's a correlation between the error terms and the regressors, the x's, then this assumption is not satisfied. And therefore, we have a non-zero expectation for some of the x values. And if this is the case, then we cannot conclude from our regression result that we have found a causal relationship. So we might say that larger classes tend to be associated with worse learning outcomes and smaller classes with better learning outcome, but we cannot conclude from this regression results that decreasing the class size by policy measures would increase the learning outcome. So this causal interpretation of the regression result cannot be done here. So the really important policy question, what would be the effect of reducing the class size ceteris paribus? So if everything is held constant, that is about the causal effect. This is what we would really want to know if we are interested in policy measures. So if we were responsible for education, for the education budget of a certain Bundesland, for instance, then we would like to know how much would the learning outcome increase if we put more money into teachers, into hiring teachers. So we would be interested in the policy effect of decreasing class sizes. That's what we mean by causal effect. And if you think back, it's really difficult to define what is meant by a causal effect, but we did that in the very first lecture. So it's the effect that we would get in an ideal randomized controlled experiment. But of course, we cannot do an ideal randomized controlled experiment in this policy setting in the real world. Okay, so this is what we defined in the very first lecture. And just to repeat that, because that's really important, because then you avoid misinterpreting regression results. So an ideal randomized controlled experiments means the following. Ideal means all the individuals actually follow the experimental design. So if you were to run an experiment with small and large classes, then you would put some money randomly to certain schools to hire more teachers, and this would really be implemented in those schools that were randomly selected. That's not really realistic, because in rich areas, the parents would just revolt against not getting the money. So in that case, not all individuals would really follow the experimental design. Then it's randomized, which means that the school districts where you put more money are randomly sampled and randomly assigned to the individuals or the districts or whatever are randomly assigned to one of the groups, to the treatment group or the control group. And finally, the control group is really important. So without a control group, you just cannot measure the causal effect. So we've done that before, but it's really important. So it's really useful, I think, to repeat that from time to time. So let's put that into the class size example context. How could an ideal randomized controlled experiment look like? And which deviations would you expect in that setting? Well, probably the treatment would not really be randomly assigned, because the lobby power of rich districts is higher than the lobbying power of poor districts. Therefore, the money would not randomly be distributed, but it would be distributed according, or at least in some association with the lobbying power of the districts. So districts with higher income, therefore, would tend to have smaller classes and better test scores. And this sounds not really important, but it violates assumption number one. That's this assumption here, and that's really the most fundamental assumption we have made. So this is really an assumption which is substantial. It's not just a technical assumption, it's really a substantial assumption. All right, and if that assumption is violated, then our estimator for the slope coefficient is biased, which means that we would systematically get a result, an estimate that is too high or too small relative to the true value. So in that case, things get more complicated, and this is where we will start next week. Are there any questions? I think we also need some feedback about the sports interruption. Because it took much longer than we expected.
Vielleicht macht es Sinn, das mehr in der Mitte zu machen und ein bisschen kürzer, weil es manchmal ein bisschen schwer ist, über 1,5 Stunden die Konzentration oben zu halten. Und wenn das irgendwie in der Mitte liegen würde und dann einfach 5 Minuten lang wäre, glaube ich, hätte das auf jeden Fall seine Daseinsberechtigung. Das
war genau das, was wir ursprünglich geplant hatten.
Ja, genau. Slots in der Mitte gibt es leider keine mehr. Oder gab es für diese Woche nicht. Ich kann mal schauen, wie es nächste Woche ist. Der 35er war der späteste, den es diese Woche gegeben hat.
Ja, wir sollten gucken, dass wir das tatsächlich in der Mitte platzieren und ein bisschen kürzer kriegen. 10 Minuten wäre ja auch noch okay. 15 Minuten ist, glaube ich, zu lang.
Ja.
Okay, aber insgesamt ist es wahrscheinlich tatsächlich keine schlechte Idee, so eine kleine Unterbrechung einzubauen. Okay, Sie können uns sonst auch über den über die E-Mail-Adresse noch Feedback geben und auch Fragen stellen. Okay, dann vielen Dank fürs Kommen und wir sehen uns wieder in der nächsten Woche. Tschüss.
Ciao.